Welcome to day 18 of the macOS and iOS Security Internals Advent Calendar. Today we will be looking at Mach Messages, so let's dig into. So Mach Messages are basically the main form of communication within the Mach part of the kernel. Basically the idea is that data is passed in between Mach ports, and it's a little bit like network packets with headers and encapsulated data, but of course it's completely different. So the implementation on the lowest level even supports different kinds of byte ordering, but in our case sender and receiver are on the same system, so these are all little endian systems, so basically all the byte ordering is usually little endian. The definition of the Mach messages is in the Mach part of the kernel, so it's in osfmk/mach/message.h. So when it comes to Mach message, it's important to realize that on the basic level there are two different kinds of Mach messages. There are so-called simple messages and there are complex messages. Simple messages are basically just a blob of data that is sent to a port without any kind of extra information for the kernel except for maybe the header. But complex messages, on the other hand, contain so-called out-of-line data or ports. So this is basically extra metadata that is passed with the message so that the kernel can handle certain special data elements that otherwise cannot be transferred via tasks, between tasks. So let's start with the simple message. A simple Mach message is basically just the message header here, and then we have an arbitrary message body that the kernel actually does not care about. So when I say the kernel does not care about, let's say the kernel message transfer code does not care about the content. There's also kernel subsystems in the kernel that pass actual messages, data, but these are separate from the actual transferring code. So the transferring code for simple messages does not care what is in the body at all. It only uses a little bit of the header to understand the content of the message and where to deliver it to. So, what is inside this Mach message header? Basically, these are the fields that you will find inside a Mach message header, and that's the bits that basically describe the features that this message uses. It has a size field. So when you actually send a message from userland, the kernel does not trust whatever size you put in there. So the kernel will actually override this field with the correct size. Then we have the remote and local port. These are basically the communication ports. So the remote port is where the message is sent to, and the local port is for the receiver of the message a hint where they should send a reply to. This can also be null, so that there is no reply expected or no reply coming back. There's also the voucher port that is here mentioned. A voucher port is basically like a cookie that is attached to a message. It is only used in various small amounts of messages. For the normal understanding of how Mach messages work and so on, just ignore that this actually exists. This is kind of advanced usage when you deal with subsystems that require these kind of voucher cookies. What's important again is, however, the message header ID, because that's something that the message transfer code of the kernel doesn't really care about, but whoever receives the message, which can also be the kernel, they use this identifier to distinguish between different kind of messages that get sent to them. For example, when it comes to Mach API, which are basically Mach messages to the kernel, they are having the routine number, the routine that you're trying to execute inside this message ID field. But yeah, for the normal message transfer, this number has no meaning. So the message bits, when you look at it, it's basically a bit field, and important here, for example, is the highest bit, because the highest bit toggles the message between simple and complex. For now, we're dealing with a simple message, so the highest bit is basically 0. Then you have the bit mask here, the 1F, 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 which basically encodes the remote mask, the local mask, and the voucher mask. And so what is that? It's basically encoding the type of what should happen with the port when it's touched by the kernel. So for example, the 19 would mean the send write of this port is copied over. A 21 would mean make a send once write, so that someone can reply once and stuff like that. A 16 would mean we are moving a receive right here. So these are all the different kinds of things that you can encode in the message itself. In most cases, it's usually 1921, so 19 for the remote and 21 for the local. Yes. So, okay, so that's the idea. This is what we need to encode inside this bits field. So now let's have a look at a complex Mach message. A complex Mach message, well, the name already suggests it, it's a little bit more complex. So first, of course, we know we need to activate the complex feature by switching on this bit here in the bits field. When we do this, we actually tell the system that we now have a specific hard-coded body. And this body is the number of descriptors that are inside the message. So we can see we have our header, then we have the body, which is just the number of the descriptors. In this case, x plus 1. So after the number of the descriptors, we then have actually an array of this many descriptors, and then we have optionally data. I'm saying optionally because sometimes you would just need the features of the descriptors and you would not need like extra data, but yes, you can also have extra data. This extra data again would be between sender and receiver, and the kernel doesn't really care about. However, when the kernel sees a complex message, what they care about is that they see, oh, how many descriptors are in there, and then they validate each of these descriptors and handle the extra metadata that's encoded in these descriptors. So what are these descriptors, you might wonder? Well, there are basically 5 defined descriptors. However, 2 of them are basically just an alias to each other in macOS and iOS. So first we have a so-called Mach message port descriptor. This is used for basically embedding a port inside a message. So this is when one task wants to send a port to another task, or when the kernel task wants to send a port to userland task. This is the only way this can be done via a message, because if you just put in a port name or so, it would not actually have any meaning in the target task, because it wouldn't know that this is supposed to be a port name, and even if it would know that, it would be actually only valid in the sending task, because they have a different IPC table. So then there is nowadays a Mach message guarded port descriptor. So the difference between the two is basically just the second one can send guarded ports. Guarded ports are kind of like a port with a secret 64-bit value attached to it that you need to be able to manipulate the port. I guess Apple needed that for something, so that's why they introduced it nowadays. But this is a quite recent thing in the last 2 years or so. Then we have the OLL descriptor and the OLL volatile descriptor. In both cases, what this is it's a way to attach an external data to the message, so that the data can be anywhere in memory and does not need to be contained inside the message itself. And then in the end, there's this OLL ports descriptor, which is basically the same as a port descriptor, except that the port is not read from the descriptor, but the port is read from an array of ports. So this can be used for multiple ports at the same time. So let's have a look at a little graphics that visualize this a little bit more. Basically, when you have a port descriptor, you want to send a Mach port to another task. And so you just fill out inside the port descriptor the name, so the port name of this port. This port name, of course, is valid only in your task. And when you send it to the kernel understands that this is a port. It will then look it up, and when the receiver receives the port descriptor, they basically get their own name filled out into this so that they can then make use of it. So this could be accidentally the same, but it does not necessarily be the same, because again they have two different IPC tables. Yes, so for guarded port descriptor it's mostly the same, but we also specify the context, which is the 64-bit secret value that needs to be transferred, so that both sides can actually have the same kind of guarded port access. OLL descriptors now, which have also an alias to the volatile OLL. The idea here is we want to send extra data that is attached to the message but not contained inside the message. So we just have a pointer and a length. So we just have a pointer to the actual data and the length of the actual data. And then the kernel knows, oh, okay, here's some extra data that we need to handle separately. The good thing doing it this way is that messages are actually quite small, and the data is external, so the kernel can choose whatever is the best strategy to share this data between sender and receiver. So that can be copying small amounts into a kernel buffer, but it can also mean for larger areas to use copy on write mappings, so that it does not waste too much memory. So the OLL ports descriptor is now the last descriptor here. And this is for sending multiple ports, especially nice when you don't know how many ports you need to send. Then you basically have a pointer to the array of ports and the count, so how many entries are in this array. So in user land, these are of course port names, and in kernel land, the port array will then be actual port pointers while it's kept in the kernel. And when the receiver receives this message, they basically get their own OLL ports descriptor filled out, and every single port it finds in there will be made available in the IPC table of the receiving task. So they will have an array of port names here that are valid for themselves. Okay, so that's the basic idea here. This is basically extra data that we need to be able to transfer ports between tasks. And as I said earlier in the ports chapter, this is also how the kernel can share a port with userland. They send him a Mach message with a port descriptor inside, and then the userland code can use this port once they receive the Mach message. So how the sending and receiving Mach messages works from userland. There's basically two Mach traps that are called. One is Mach message and the other is Mach message override. There's also something new in very recent version of macOS, like Mach message 2 or so, but we ignore this for now here. We just want to understand this here before we go to other kind of deeper knowledge. So internally, Mach message sending looks a little bit like this here. We have a userland part and we have a kernel part. And in userland, we have libc functions like, for example, Mach message or Mach message override, which are basically direct wrappers around the Mach traps in kernel land. So you can see Mach message is basically Mach message trap, and Mach message override is a Mach message override trap. Here you can also see that Mach message trap is basically just a wrapper around Mach message override trap. In any case, this is the direct usage of sending messages, but inside libc there's also something like Mach message send and Mach message receive. They both use the Mach message libc function, because you must keep in mind that the Mach message trap or function is capable of sending and receiving, but these functions here can only do once. The next thing is also that when you have Mach API or so functions or MIG functions in userland, what they basically do is, for example here host info, what they basically do is they take the C-level arguments to the function, turn them into a Mach message, and then send them via Mach message to the kernel. And so basically all the Mach API in your library will do exactly that. They will take your parameters, turn them into a message, send a message, and then later pass the result and return the content of the return message. Okay, anyway, so let's skip the userland part, go to the kernel. So we have the message here, and at some point after a lot of work, it will call something like IPC kmessage send. And this IPC kmessage send will basically attach the message to the message queue of the port. So this is happening down here. And the message queue by default is 5 entries long, but this can be changed via APIs. And the idea is that if you send more than these 5 messages, it would then block until the message queue is emptied by the receiver. So in this IPC kmessage send, there is, however, a detection in there. If the receiver of a port is actually the IPC space of the kernel, then this is assumed to be actually a Mach API call, and it's assumed to be a kernel object port. In this case, it will call the function IPCK object server, which is basically the handler of Mach API. It's a dispatcher for Mach API. And what this basically does is it looks up what the implementation routine for a specific Mach message is. It does it by looking up the message ID in a hash table, and then it will call that routine, and the routine will work on the incoming message. The routine will pass the message, execute the implementation, take the return arguments, turn them into a reply message, and then the reply message is basically by changing the local into the remote port. What happens is that it also goes to IPC MQQ send, so it will basically enqueue the reply into the message queue of the local port, so that the local port now contains the reply to the Mach API. And whoever receives this then, usually the userland function does it immediately, will then read from the local port this reply message, and then it discards it from the kernel, and this ends the basically Mach API call. Yes. So let's have a look at how this looks in real world. So this here is how you send a simple message. You use the Mach message call. You tell the call that we want to send a message, You specify how many bytes this message has. You tell the system where is the buffer of the message. And then you specify the buffer size for a reply, the port for reply, the timeout, and the notify. But all of this is not used right now, so it's all 0. And what we are doing is we're sending a message that looks like this here. We have a header and then a body that's like 100 bytes. So we first prepare the body of the message, then we fill out the header, and the header basically, the remote port is some arbitrary target port. We could have created that ourselves with Mach port allocate. The local port, we don't need a reply, so that will become null. And then the bits is basically we make ourselves a send write, and the 0 means no rule for the local port, and there's no complex bit set because it's a simple message, so that's everything. Here we also fix the message header size, message size in the header, but I told you earlier that this is actually discarded by the kernel because it cannot trust what the user then writes into this. So this is later filled out by the kernel anyway. Yeah, and then we send the message, and what can happen here is that there's a problem, so it immediately errors out. It can also happen that it returns with no error, which means the message was enqueued, but it can also just block in case the message queue for the receiver is full, basically. Yeah, so now how do you receive a Mach message again? So this you can do by basically telling the system to receive the message. You have no ports to send something to. You have no bytes to send. You have a buffer of 5,000 for the incoming message. You have a source port to read the message from. You have no timeout, and you have no notify. And then you basically read the whole message up to 5,000 bytes in the message in buffer. So if you exceed the 5,000 bytes, you would run into trouble because that of course would result in an error condition. So how this should be handled is then configured via the flags inside this here, and you have to look into documentation for all the different kind of options. So one of the options, for example, is just to return error. Another option is to read back the first 5,000 as a peaking, and there's potentially some other newer things that you can do here. In any case, all the different things in the bit field here, you should look them up in the documentation, because there's way more than we can cover here, which can be controlled via this here. Because it's a bit field, by the way, it's also possible to send and receive a message. When I say send and receive, it's important to realize that the logic here is always send the message first and then receive some reply from the port specified here back into the same buffer. That's basically how send and receive at the same time works. So you can only always send and receive. You can never receive and send in one. It's always send first, then receive. So now that was how you do it for sending a simple and receiving any kind of message. Now let's have a look at a complex message example. And what you can see here is that we also have to fill out the header, which is more or less the same as before, except that we now set the complex bit here so that the kernel knows we're actually sending a complex message here. And then we basically fill out the body, which is the descriptor count, to, in this case, 1. And then we fill out our descriptors. In this specific case, we are sending an OLL ports descriptor, so we're actually trying to send ports to the kernel. And we have to specify the address, which is the port names array pointer here. and the count is 7. So we have actually an array of 7 port names in some userland array, and we want to send this over. We tell this is an OL ports descriptor, and we can see here we also have to fill out the disposition here, which is like move the send right basically in this case. And then we send the Mach message in exactly the same way, only that this time the Mach message has basically a descriptor attached to it. And yeah, that's basically the whole idea. And now you can receive this kind of message in exactly the same way as before. Only this time when you receive it, you should have also a descriptor count in there, and there should also be an OL ports descriptor, and you will have filled out this information, which means there will be something allocated in userland to hold the port names array, and it will have 7 entries, and these 7 entries will be ports, the same ports that were sent, but this time made available to the receiver's IPC table. So there will be different port names, well, let's say very likely different port names, but theoretically there could also by accident be exactly the same port names. Just because different processes have different IPC tables and different gen counts in their indexes, so that's why it will likely be different port names. Yeah, and that's basically what we're covering here about Mach messages. This is all you need to know to understand how sending and receiving Mach messages work. And this closes our day 18 of the Advent calendar. I hope you enjoyed it. See you again tomorrow for day 19 and door 19 of the calendar.